Alrighty, let's get started. So welcome to week one of the IEEE PCB design workshop. Today we're going to cover an introduction to schematics. If you're an electrical or computer engineer, you've probably seen these in your circuits classes. This is actually digitizing these, having a digital representation of these so you can actually turn these into boards. This is a skill that's not quite taught in our current department. The PCB course, unfortunately, this semester was canceled. So right now we're kind of covering and filling in for that. So if you do want to have an actual course and get course credit for doing PCB design, maybe bring that up to the department. Last year it got canceled because department drama and not enough interest. Clearly there was more interest than there was for the signups. So my name is Adrian Sachayo. I'm currently the IEEE chair. I've hosted this workshop in the past with Nick Howard over there, who's currently not going to be teaching this semester, but, you know, you can maybe pester him. Can we pester you?
No.
Oh.
No, yeah.
It's fine. All right. But this was structured after what we did last semester, and yeah, let's get started. Here's the outline of the workshop. We're going to be scheduled for about 9 weeks. Most of the bulk that you'll learn in Altium is going to be between now and October 1st. This is where you're going to be learning how to do schematics, make up parts, actually draw these things, convert this into a PCB, do layout, verification, rules checking, and then finally, if you finish by our deadline, we will have your board manufactured. So you'll send us your final design files, we'll send them off to JLC PCB, and you'll get these boards back for the second half of the semester where you'll learn how to solder them. We'll provide all the parts for you, which is really nice. Hopefully ASUU will give us our money. If not, the fees for this will probably be pretty small, maybe like $5 at the most, I'm hoping. But last year we were able to get everything covered by ASUU, which is our student government if you're not familiar with them. So yeah, and if you have any other questions, you can bring them up later. During the second half, we'll be doing soldering. We won't meet in here. We'll probably do different sessions throughout the week, so you can choose time slots that fit you best. We only have a limited number of soldering stations available, so we'll have to divvy out who gets to solder when. So there'll be a sign up for that when that becomes more relevant. So yeah, some logistics. We highly recommend attending all workshop sessions because they will technically build off information covered in the previous sessions. If you do miss a session, I'm hopefully recording this. I don't know. I'm using OBS. I've never used OBS before. Hopefully it's capturing everything correctly and recording me, so you'll be able to follow along. All the design files we posted on a GitHub. If you've received my emails, the most recent email has the link to our GitHub. I will also have the link at the end of this presentation when we start getting into design work. So, some objectives. By the end of this workshop, you should be able to build an adjustable USB-C breadboard power supply. It's actually a pretty neat project based off the stuff we did last semester. There are some improvements that we've made to make it a little bit easier to assemble, and it has some extra features that make it a little bit more useful for you and your labs because it's a breadboard power supply. I assume many of you on your circuits labs are using the bench power supplies. If you have any other projects, you can use one of these. You'll gain some experience doing schematic layout, PCB layout, and learn how boards actually get manufactured. And you'll gain some experience in through-hole and surface mount soldering. So we're going to be mixing the two. I believe some of you have through-hole soldering. Some of you are BGA demons, which you guys scare me. I don't do BGA myself. You do BGA. You're scary. Anyways, so you'll gain some experience doing some basic PCB assembly, and you'll basically have a preliminary understanding of how PCBs are made in the industry, and you should be able to make your own stuff, which is pretty neat. Going back on fees, we hope to get our funding from ASUU. I put in a pretty large request that should be able to cover this session. I will fight ASUU if they don't give us money, so hopefully they do. And we will know at least by the beginning of October if we will need to charge fees. So that's where we stand currently. And I know a couple of you are part of some other organizations or you already have like a background in PCB design. So if you want to pursue your own personal project, you can talk with me or message me, email me. We can maybe get your board manufactured if it stays within the 10 by 10 centimeter limit of JLC PCB, and you'll get that instead of the USB-C power supply. We won't be able to provide parts for that, but at least you'll get your board manufactured for almost free. You won't have to pay shipping on that, so it's a pretty neat opportunity if you want to pursue that. I need to shill. Nick Howard and myself are technically attractive. You're more of a lead than me, but we're both on the attractive team. It's the elective team for the Formula SAE or FSAE club. Will, I'm sorry. I'm so sorry. Will is also a high voltage person on the FSAE team. We're basically the old guard. But we're looking for new people. We actually meet directly after this workshop in MEB. So if you have some extra time and you'd like to get some hands-on experience doing some more board design, no experience is necessary. We'll help you get everything online. Do you have anything to say?
You should definitely consider joining. You'll get a lot of applicable experience you otherwise wouldn't get in school. Experience on this team and in PCB design was probably the main reason I recently landed a job. So I just highly recommend getting this useful experience you won't get in school.
And then there's a QR code there. These slides will also be posted, so if you don't have it right now, you can find it later. It's probably, I think it's also just listed on the university clubs list if you're on that as well, if you wanted to share your email with the Discord, but that's a personal choice. And next off, we have the IEEE Discord. I will be posting some announcements there. There's an announcements channel. If you want to stay connected, that's where a lot of the ECE people kind of hang out. It's a very quiet server, so it's not too much of a burden. It's not like the CS server. There's little drama. We don't talk about the CS servers. So if you're interested in joining that, the link is there. And these slides will also be posted afterwards, so you don't have to scan it now if you don't want to. So, any questions before we get started? And take that as a no. So, what is a schematic? Schematics are graphical representations of an electrical circuit or system. So they're a step up from block diagrams, which you may or may not have seen, which are basically logical organizations of similar blocks that you just connect together. It shows all the parts and the electrical connections in the circuit. So any wires, essentially, that you've seen in class would be represented here in a schematic. These are also used as the guidance for PCB traces during your layout. What is important to note is schematics are not the physical representation of your circuit. You can draw your schematic however you want. It could be physically impossible to build this thing in real life, but it could be a schematic representation. That's the beauty of these things. Make it nicer to read. That's the main advantage you can do because it's not physically accurate to reality. So in the schematic, you'll have components. There's a little graphic on there that has all the components that you might see pretty commonly. So you have like resistors, capacitors, switches, voltage sources, all your different types of transistors. Many of you have probably seen these in your circuits classes, and they are still going to be used here on your schematic in Altium. It contains all the pins that are connected to component. There may be some extra information. So you have some stuff called like designators, values, part numbers. There's a bunch of other information that you can have on there. We'll show you in a bit. And they're pretty consistent across all different ECAD softwares. So if you're using Altium, which I highly recommend you do because this is one of the few opportunities you'll get to use Altium for free with your tuition. And it's very commonly found in industry. Nick Howard uses it in work. I use it at work. It's a pretty good software to get some experience in. Put it on your resume. It's great to see. If you guys are using KiCAD, the concepts are translatable, but we will be demonstrating Altium for the purposes of this workshop. And moving on, we got symbol attributes. This is what I mentioned earlier. So it's like the designator, values, part numbers, part names. So you can kind of see here. This will be important later on when we do a PCB layout. You have part number, you have values, and then all the different things that are represented by resistors. And you'll see a lot more of this once we actually get into the layout itself. One thing to note is there are US and international symbols. It's kind of willy-nilly. You'll see both of them in industry. I personally prefer the international symbols, although I do draw my hand circuits with the US symbols. So you'll see like resistors are represented by a box instead of a squiggly line. In some of your classes, you may also see the box represented as an impedance. That's where it gets a little bit tricky because you can't really have an impedance on a PCB represented by a component. It'll be either a physical trace or physical resistor. So it's just something to keep in mind. So those are just some of the differences. The capacitor on there isn't a great representation of the international versus not US. The polarized one and the non-polarized ones typically will be both rectangular in the international standard, like the one on the left. But you'll see the differences when we actually get into the layout. We're going to talk about nets and nodes. So in your circuits classes, whenever you draw a line and a connection between two components, that line, that wire, that physical connection is called a net. It is very important to keep your nets in check. These are important because they show how things are electrically connected in your circuit. And then there's concepts called junctions, nodes and junctions. This is where you might get some errors in your PCB if you do this wrong. So a junction is basically the connection between two different wires, and it will basically connect everything that's denoted in a single net. If you make a mistake in your schematic and you don't actually have a junction show up, it will not be connected in your PCB when you do layout. You'll manufacture it, and now there's an error in your board. So make sure you double check all these connections. You can see on the right over there is a zoomed in version of what a junction looks like. The Altium default doesn't do that little hop over the wire. That is a preference setting that we can talk about if you're interested in getting that. It'll just look like a T without a dot. The dot means it's connected, the jump means it's not. Or a cross without a dot means it's not. So be wary of that. Another concept is net labels. In Altium, whenever you connect wires, it'll generate a name for that connection. That connection will be called like C1_1. What does that mean? There are some patterns in there. It's component C1 on the first pin. There is a hierarchy to how it assigns it, but you can explicitly denote these. So net labels allow electrical connections to be made without having to draw lines between components because a net represents all the electrical connections between the components. So you can see there's a bunch of different signals like LED indicator 4. There will be another component with LED indicator 4 somewhere else on the board. Those are electrically connected, even though they don't look physically connected on the schematic itself. We will only be covering labels currently just because our board is a single layer board, or not single layer, single board, not a multi-board project, not a multi-sheet project either, so we don't have to really talk about ports. But ports are useful in something called hierarchical design, which helps you basically organize much larger systems. And if you have any questions about that, I can also go into that after we get stuff through. So, any questions about that spiel before we move on? And tell me if I'm moving too fast, because I do talk a little quick sometimes. Anyways, good schematic practice. Readability is key. Like I said earlier, this is not a physical representation of your components in space. You can make things that are not really gonna work if you tried to build it in real life, just because there are some reasons for it. Just make it readable. If you don't make a readable schematic or a legible schematic, sometimes other people will get mad at you, or you will get mad at yourself when you have to debug a problem in your board, especially as these boards get a lot more complicated. You will have to figure out, where is this signal, where is this logically organized, what am I trying to find? So as you can see, that's a nice little graphic of what not to do. If you know XKCD, that's where that comment comes from. So some tips. We as humans in the West, we read from left to right, so sometimes it is valuable to logically populate your schematic or logically organize some of your circuit systems left to right. Do not overcrowd your circuits. You have a digital plane. You have a lot of space. If your schematic sheet is too small, make a bigger one. This is not a physical piece of paper. You can move things around after the fact. You guys with iPads, y'all know the feeling when you're just resizing your text. You can do that kind of here. Not physically resizing, but moving stuff around. Another tip is to use logical blocks. So circuit elements that are connected logically or related to each other should be pretty close to each other. For instance, if you have an LED and you have a current limiting resistor, you want those to be pretty close because that current limiting resistor is very relevant to that LED. You don't want them on other sides of the paper. Keep them together. There are also some stuff to follow from manufacturers. So Texas Instruments, ST, NXP, all these manufacturers will typically have some reference layout for a lot of their stuff, especially as you get into more complicated systems like microcontrollers, switching supplies, which is what we're going to be designing. So we'll be referencing that. It gives you a layout of what the manufacturer recommends your circuit should look like in order to be logically readable. Label your signals. Sometimes a signal is unclear. You can put a net label on things that will still be physically connected on the schematic. It's really important if you have key signals to denote those just so you don't lose it. It also helps with debugging, so it's just something to do. And also power. There are things called net labels, or not net labels, power nets. Those are basically your 5 volt, 12 volt, voltage in, voltage out. Those signals typically are organized positive at the top, ground at the bottom. Sometimes you'll see something funny, you flip a ground upside down. Don't do that. It's not great, because logically things flow, current flows down through your schematic. So it's better to keep that all together logically organized. So here's some examples. This is from last year's presentation. Who can tell me what's wrong with the first one? One on the left. Yes. Okay, ignore those little X's. Those X's are error suppressions because it's technically not connected to anything, just for the purpose of demonstration. Yes. Yeah, it's jumbled, right? So you see how aesthetically pleasing. What's wrong with the second one? Yeah. Yes. So you can see, especially here, this junction is literally on the node of the capacitor. You can stretch that out. It's not great practice to put the end of a component in a junction. Just because sometimes you want to connect over it, it'll override some stuff. Just don't do that. And the third one, is anything wrong with it? Pretty standard. It looks pretty good. Not bad. Good job. But anyways, yeah, that one's pretty nice. The components are lined up very nicely. And if you don't recognize this from your circuits class, this is, I think, a class A amplifier, single BJT. I could be speaking wrong. It's some sort of amplifier, but that is a standard configuration for one of those. So if you know what a circuit element or circuit system is supposed to do, and there's an established literature around it, try and follow how that's written in, in the industry. It helps with debugging. It helps other people read your schematics. Pattern recognition is a really big thing with schematics. So just keep that in mind. So any questions about schematic tips before we move on a little bit? Alrighty. ECAD software. So I've been referencing ECAD. ECAD stands for Electronic Computer Aided Design. So you may have heard of like Fusion 360 as a CAD software where you're doing physical mock-ups of things. It is also a very good skill to learn. Use your student license now. And there are many different ECAD softwares out there. There's Altium, KiCAD, Eagle, OrCAD, EasyEDA, if you guys use that. EasyEDA is pretty lightweight until you start doing more complex things. Then you should switch to a proper ECAD tool. KiCAD is free. That's what's great about it. It's open source. It's still in development. KiCAD 9 is actually pretty nice. Please don't touch Eagle. There are reasons why I avoid it like the plague. It is a hodgepodge of Autodesk and Eagle when it was an independent organization. So there are a lot of oversights that really do not work with CAD software. OrCAD, I've never personally used, but you can also use it for PCB layout. So we're using Altium Designer mostly because we all get student licenses. If you all haven't followed those steps to get that, please follow those and get your license. Unfortunately, it only does run on Windows computers as far as I know. But if you want to follow along and you still want to design a board, you can use KiCAD. I have some files up for KiCAD that are basically ports of the Altium files. However, I won't be able to support you as much if you do have issues with those, just because most of the stuff is written for Altium. and I just explained myself. So yeah, job application. Get this on your resume. It's a really good thing to see people have actual experience with tools that they will see in the industry, because you're going to be a new engineer someday, hopefully, or whatever you work in, and they don't want to teach you from the ground up sometimes. If you have experience, it's easier for them to bring you on board. It's easier for you to understand what they're trying to do quicker, and that's more attractive for them to hire you. So yeah, any questions about ECAD software? Or KiCAD or Altium or any of those? Alrighty, so I'm going to introduce the project. We're doing a USB-C breadboard power supply. So we're going to have two different supplies, because there's on a breadboard, there's two different rails. You'll have an independent supply for each of them, and there's going to be a switch where you can either use them isolated or in tandem together. There's going to be two different inputs that you can use, a primary and a secondary. The primary supply is actually going to have the USB power delivery trigger board, and an initial barrel jack, so you can power this either with a wall, or if you have like a laptop with the Type-C port, it should be able to give you your full 20 volts output, or whatever your charger is capable of. And then there's also some output bleeder resistors that help to discharge the output capacitors, but that's something we can talk about once we actually get the schematic layout. So I mentioned earlier about block diagrams. So this is like an overall block diagram of what we're going to be doing. You can see the two power inputs and the power delivery input. There's a power input selector, two switching regulators, and the two outputs. The reason why I have this up is one of the more important things to get in your mind before you start laying out things is what you're trying to achieve. And then once you know what you want, you can then spec components. You can go to Mauser or DigiKey or whatever supplier you'd like and start searching for components that fit those requirements. So I have defined the requirements already just for guidance, but the power inputs. So we're going to be using a terminal block input. You might have seen these. These are use a screw to put your wire in and then you clamp it down. It's not the best connection, but hey, they're cheap and you'll find them a lot. So they're pretty easy to use. There's also going to be a barrel jack input, a USB-C power delivery breakout, and it'll be 20 volts max. So you'll be able to regulate some 20 volt supply down to, I think it goes down to about 2 volts is the spec on this supply. Does anyone not know what PD is in terms of USB-C? Yeah, so PD is power delivery. It's a standard for basically communicating between the device and your charger about what the capabilities are. So USB-C is capable of doing 5 volts, 9 volts, 12 volts, 15 volts, 20 volts, and I think the newer standards go even higher. So you need to have some sort of communication between the charger and the device. We have a board that will basically say, I want 20 volts, give me 20 volts, and then the charger will try and comply as high as it can to that request. So we won't actually design that board ourselves. There's a little breakout that makes it a lot easier to install. But that's what USB power delivery is. There's also going to be an input selection. It's just going to be a big switch, which allows you to select between the primary and secondary supply, so you can isolate both the left and the right, or supply A and B, which I'll show you later on in the schematics. And then the supplies. We are going to be using a switching supply. Many of you, or at least some of you, may have heard of linear regulators. So there's some jelly bean components like the 7805, 7812, 7815. Those are linear voltage regulators. They're very inefficient. They convert any extra voltage or energy into heat, which in a power-constrained system is not desirable. Or if you're stepping down a large voltage like 20 volts to 3 volts, you're cutting down 17 volts. If you're pulling an amp, that's 17 watts you're going to have to dissipate. A switching regulator has some advantages. It's a lot more efficient. You can handle quite a bit of current with these. And this particular part, the LM2596, is really nice because it's part of a line called the Simple Switchers from Texas Instruments. So there's a lot of documentation. It's a pretty old chip. It's a very good jelly bean component as well if you are interested in building your own power supplies for your boards. Just because it has a pretty high output capacity of about 3 amps. So that is what the actual part looks like. It's 5 pins. And then the reference design is going to be that on the bottom. And then finally, power outputs. So we're going to also use a pin terminal, not a pin terminal, a terminal block in, I should say output. Output We also have pin headers. So this board is designed to be the same width as a breadboard, so you can just stick it up. You don't have to mess with any of those funny DuPont connectors, no wires. You won't have to deal with any of that. So it'll be nice and easy to use. And there's also going to be output bleeder resistors. Those just help make sure the supply can discharge. So if there's no load on your supply and you turn on the voltage, it'll take some time for that capacitor to discharge down to your target. These resistors help do that faster. And they're configurable. You can either use them or not. It's really up to you. So, any questions? Yes? Okay, jelly bean is basically a part that's really common and established. So in your circuits labs, you may have heard of like the LM358. It's an op-amp. That's considered a jelly bean component because it is like an op-amp. If you just need the basic functionality of an op-amp, you choose that component. But if you want to do something more specific, let's say you need very low null or very low offset or high input impedance on your op-amp, don't use a jelly bean component. Find a specific part that will fit your needs. But for the most part, especially for hobbyist applications where you might be doing your first or second board, jelly bean components are pretty good. You can also buy a bunch of them just to have on hand so you can prototype pretty easily. I think the stockroom sells a lot of jelly bean components just because that's what you're likely to use in your circuits labs. Does that answer your question? Perfect. Any other questions? Take that as a no. And you can always ask me questions after the fact, but you're all good. So we're going to actually open Altium now. So we're going to navigate to the GitHub and download today's files. Actually, don't download today's files. We will start from scratch. But you can pull that up. I sent everyone the GitHub on their emails. So if you didn't get that, the link is up there. Keep that for further reference. We'll be continuously updating that as the weeks go by with the current materials and anything that you might need for the workshop itself. And then also while you're doing that, let's open Altium. Stop. And something to note, if you do not have a mouse, I recommend using a mouse with any ECAD or CAD software. Trackpad is not the way to go. It is pain. Unless you're a trackpad demon, get a mouse, please, and save yourself the hassle. Alrighty, so everyone's going to start their own project. This is something that you'll be working on through the next couple sessions, so keep this in somewhere that you'll have access to and won't lose. The reference files are on the GitHub, so you can import those into your project just to reference, or you can open those just to look at them. But I do recommend, if you can, to have your own project up and running just so you get some experience doing actual schematic layout and all that stuff. So we're going to get started and we're going to do a new project. So you should see something kind of like this, just a home page if you have Altium. KiCAD, it might be slightly different. You might see like nothing. But we're going to make a new project. So you're going to go File, New, and then Project. And you should get some window like that. And then once you're here, there's a bunch of different options. You can do a multi-board design. You might have some templates in here. If you're doing a wiring harness, Altium also supports that. I've not used it personally, but could be something to explore. FSAE. So we're going to start with just an empty PCB project. You're going to name your project something memorable. You can call it USB, C, power supply. I'm going to save mine different. So this is I can save mine. And then you can use the three dots here to choose where you're going to save it. I'm going to save it not in the Git, but I don't know, in document somewhere. And it cleared my name. That's great. So after that, there are a couple parameters you can add if you'd like to add like your author name and stuff like that. We won't deal with that right now. You might deal with it later, but for now, let's just ignore that and click Create. So on the left-hand side, you see this pop up. This is your project file. If you left click or right click and you click Explore, where the hell am I? Oh, I'm not saved. Oh. I don't know where that is. Okay, maybe don't do that yet. But this is basically how a project is organized. You'll contain all of your schematic files, your PCB files, any of your rules, any of your bill of materials, and manufacturing documents will be present within that. Reference design up here, that already has some stuff in it, but we're not going to use that right now. We're going to start with something blank. So today we're going to talk about schematic layout. So we're going to right-click on that, add new to project, schematic. And it should create a nice blank sheet. And this is where you're going to be doing a lot of your work. In KiCAD, there should be a couple other places where you can add it. I'm not great at KiCAD, but there should be a similar button. But this is where you're going to be doing a lot of your work. This is where everything regarding your schematics is going to be done. There's a toolbar at the top. This is where you're going to use a lot of shortcuts. So wiring components, any symbols will be probably present up here. On the right-hand side, I'm not sure what the default looks like, but you might have a button that says Properties. This window is going to be pretty important. You'll reference it a lot, and it depends on what you're selecting. So right now, there's nothing being selected. So, we don't want that. It's just going to be the properties of the schematic diagram. So here you can set a lot of different things. You can set like the grid snap, the visible grid width, how large your sheet is. Though right now it's an A. You can select all these different ones. Like you can be a legal size, A4, A3, and a whole bunch of other ones. There are templates out there. You can make a template and it'll basically change how this looks. So for example, you can use like this. So put like some extra information in the bottom, but we're not going to deal with that right now. We're just going to do something basic. So you're going to have a standard, and I'm going to use an A3 just for the demonstration. You can choose something else, but A3 is what I prefer. A couple other things you can add to these standard ones is have a title block. So this will add that little block in the bottom. It is a blank. You can populate this with text later on. And something I do like is a sheet border, just so I can see the edge. And these are all contained within the properties window. So that is what a schematic sheet looks like. We're going to save this project now. Oh, there we go. So when you save that, you'll get to name it. I'm just going to name it schematic. But you should probably name it something a little more recognizable. So you could call it like USB-C mainboard. Yes. Okay. Yeah, so first off I did File, New Project, we got there, and then we right-clicked on this part over here, and we're going to say Add New to Project Schematic, and that will bring up a new blank sheet. With that sheet, we want to basically select how big we want it to be, so I want it to be an A3. I'm not sure what the default looks like, but there's this properties panel you can get up here. If that doesn't show up, there is in the bottom right corner this panels button. If you click on that, there are going to be a bunch of things in here. There's one that says properties. Click on that, and then it should, I deselected one. It should bring it up. And then in here, we're going to change, you don't have to use a template or a custom, so we're going to stay standard. Sheet size, I'm using an A3. I wanted a title block, and then a sheet border, which is the option up here. And that's, title block is here, yeah. I wish I could zoom in. Yeah, once you all have that, anyone's stuck. Right. So you're going to save that document if you haven't already. You can right-click on that, press save. There's also file save, just like any other software out there. It's pretty standard. But now you should have a document that's ready to go. I'm going to first introduce some of the tools that you're going to be using to basically wire things together in the top toolbar, just so you have an idea. And then we're going to talk about libraries, where you're actually going to get your components to put into your project. So in the top, there are a lot of buttons. You might not know what they are, but these are basically how you interact with everything on the sheet. There's a selection filter. So there's different types of things that you can put on a schematic sheet. And you can filter the selection. So if you just want to select components, you can filter just select components, and you can click and drag a little selection box over it. It select all the components. And it's the same for all of them. We're going to leave them all enabled. This is very useful in PCB layout in that step, so just keep that in mind. We don't really use these other two. They're just drag objects. There's components, so place part. This will open a new window on the side. Sometimes you can just go directly to the side and place a component. Altium does have a built-in cloud library, I believe. So you have you can select various capacitors and whatnot, but it's a very limited selection, or they're very specific to a manufacturer. So I don't know what the ECA1HM2R2 is. We can click it, double click it, and add it to our sheet. And we have a component. So these cloud components are managed by Altium itself. If you work in a company, sometimes you'll have someone dedicated to managing your company's library, which will have all the components and footprints that are relevant to your organization. For us, since we're really not part of an organization, we're going to be managing our own libraries locally. So I'll teach you how to import some of those. But just for now, this is how you place components for the most part. So I'm going to delete that. Or actually, I'm going to keep that. And you can select any of those components if you'd like. Next to that little yellow bug-looking thing, you have place wire. Wires connect things together. I'm not supposed to do that. Why is my snapping? I'm gonna. Well, schematic is this. Don't mess with your snapping distances, please. Okay. Let me put that there. So you have these components. So wires are how you connect things together. If you look very closely at each component, you can zoom way in. If you don't have a mouse, hold Control and scroll. If you have a mouse, little mouse wheel, you can hold that in. Hence why I recommend you use a mouse. You will have to use a keyboard a lot if you're using trackpad. But if you look really closely, there's a little, 4 dots. That is where you're actually going to connect your wires. So if you hover over it, you should get a little X. That means this wire is now going to connect to this component. If I put it here, oh, don't snap to that. If I put it here, this wire is not actually connected to that component. This wire is. So it'll reroute itself sometimes. Sometimes it's a little finicky. I'm not sure the exact rule of what it prioritizes in terms of routing. Sometimes it'll just steal your wire away. Sometimes it'll try and reconnect it as you drag the component out. So when you're doing a schematic, make sure you actually connect your wire to that point. It may look connected. If you're not actually connected, you're going to have big issues later on. So that's wiring. There are a couple other things in here. So if you right-click on that, looks like 2 wavy lines. You can see different stuff in here. There's buses, bus entries, net labels. We're not going to talk about buses in this workshop just because there's no real need for a bus. But a quick overview of that is just a way to group a bunch of wires together and route them together instead of having to draw, let's say, 8 different wires on an 8-bit bus. You can just draw one bus. But there is something useful in here, net labels. These are how you add tags to wires. So if you look at a net label, I'm going to do that again. Your cursor will be on where it's going to try and connect. That's going to be where it's actually going to enforce its label. So if you go to a wire, I'm going to draw a better wire. If you have a wire, you can see it forms a little X on the ends, but as long as you're connected somewhere on that wire, you can click. You can see a little dot here that indicates that this object, this net label, is actually on this wire. So now this wire might have, yeah. If you click the wire itself and you go to properties, you can see now it's called column 14. And what's kind of nice about Altium is it will remember some of your old stuff, so that's from a different project. But if you want to change the text, you can either place a net label and type in a new name. So this is like my net. You can change the placement of it. So relative to this little dot, there's this little DDR pad, let's call it, that lets you place it relative to that point. So I prefer it like this. You can flip it around and do this and align it towards the end of the net. But that's how you do one of those. I will introduce another concept here, which is pausing. When you have a wire or a net that you want to place, so let's say I want to place a new net or a new net label, I can hit tab, I get this pause. I can now edit all the properties of this object before it goes down. So this is very useful for a lot of repetitive things. If you have numbered things, so this is like column 15 now, it used to be column 13. If you have a number at the end of your net label, it will auto increment then. So if you're labeling like a bus or a collection of wires that are numerical, this is a great way to do it just to save a lot of time. So I'm just going to call this net 0. And then you can watch as it nicely auto increments. So those are nets. There are power ports. I mentioned these earlier. These are pretty much standard. They help organize things so you don't have to actually draw the voltage connection between all the components. So some of you are familiar with seeing like a +5 volt at the top of things. There's also ground in here. There's many different grounds, but these act essentially the same as a net. So if you click on them, you can have a property name, so you can have those like analog reference. And every net label that is labeled A ground will be connected. Power ports are also special if you're doing multi-board design because they're global. Net labels are local. So anything that you name on a local sheet will only be relevant to that sheet. Global things will be translated across sheets unless you have a specific setting turned off. So by default, if you have multiple sheets with a 5-volt rail, that 5-volt rail will be shared amongst all the sheets. And those are that. We're going to skip the harnesses and the sheet symbols. There's ports. Ports are not really relevant to us, but they're good to know for multi-sheet as well. They can indicate signals that basically leave the sheet and connect to somewhere else. If you have multiple ports, it will, by default, Altium will have a little indicator next to them of what sheet it connects to, so you can reference it in a bigger diagram so you know where to go. We're not going to talk about those. Those are error blankets. Those are not very relevant right now. And then we have text. Text is also kind of important. It helps you logically organize things together. Similar thing with net labels, except these won't actually assign anything to a wire. What's important is don't mix up your net labels and your text just because you're not actually labeling your wire. It's text. There's different types of text. There's text frames and notes. Notes are like a little post-it note that you can put on a diagram, and you can put, you know, in these, you can collapse them. So basically a sticky note. And then we have lines, arcs. These are a bunch of graphical things. The one that you're probably going to use most commonly now is the line tool. This allows you to draw lines. These aren't actually wires, so they won't give you any errors of being, hey, I'm not connected, because it will throw errors if things are hanging. You can change the style of these, the thickness, the line style, the end shapes, but that's something you can explore as well. The final thing we really don't use because that's for simulations. We're not going to be running any simulations. It's a switching supply. It doesn't really work that way. So any questions before we start moving into the parts library and actually start building our circuit? Yes? It's on the GitHub. Any other questions? Yes. Yes, it should. Hopefully it's recording. It seems to be recording. Maybe like 10 more minutes and they're going to send you off. Because the next session is going to be more, just as an overview, next session is going to be, I'm going to continue talking about parts and how to make your own parts, and it's going to be an open work session. So anyone who needs help actually building their schematic, attend that session, and then we'll be able to work through a couple things. So if you do have to leave, next time is going to be a lot of work, if that makes sense. All right, any other questions? Oh, all righty. So I'm going to, that's not, you can go to the workshop files, and in the master design reference, there should be an Altium component library folder. And if you haven't pulled that down, so you can pull down the entire repository, and then all your components will be there. So let's actually add that to our project so we can access it. Or how many people have not found that file? All right, I'll give you a second. All righty. So we're going to import that library. So many of you have probably downloaded it. The file that we need today is going to be the schematic lib. So this file, that's all we really need for today. Ignore the lib package. It won't work on your device because it's referencing files in my directory. Well, we can talk about library management next time. So take this file. You could technically leave it wherever you downloaded it, but we're going to put it in the same directory as our actual project. And I'm just going to paste that. So this file contains all the information for each of the symbols that will be present in our schematic. These are things that you can make and manage yourself. I don't want to open that, but that's just a preview. My mouse double clicks. But yeah, this is a pretty important file. You can have multiple of these per project, but since our project is simple enough, we just need one of them to manage the entire thing. So once you've put that in your folder, you're going to go to your schematic sheet or back to Altium. You can right-click on the project itself, and then you're going to add existing to project. And then that should open up the same directory that you were in last, which should contain like the schematic sheet where you saved it. And you can click on this and open it. And now a new folder should appear with this library attached to it. And you can double click this. It'll open up and it'll show you all the different parts that we're using for this, this project. It's all already made, but we'll teach you how to actually make these next time. So if you do have your own custom projects or different components, you can actually make a symbol for yourself, because that is a skill. We might have to make some for FSAE, unfortunately.
Wait, what?
Well, you're not finding your Molex connectors.
Oh, that's true.
So, well, we'll figure it out. But yeah, once that's imported, you can save the file again. And I just save all my files. Anyone have any issues referencing or importing that into their schematic? Alrighty. And then, now we're going to look at how to put components. So if you click the components button again, you should be able to click on this drop-down menu up here, and you should see the name of our schematic library. And if you click on that, you can see the list of every single part that we have in the schematic. And you can try clicking on one. So I want a resistor. Here's a resistor. I want a potentiometer. Nice. So all of these this library contains every single part that you'll need to actually do the final project, or the power supply project. And the one project that, or the one schematic that you're going to be trying to replicate is this. This is basically everything that is going to go on the board. And we can go over this. I'll go more in depth on how I made this last time. But if you would like to try and make this between now and next time, by all means, try it. Get some experience actually putting components down. If you get stuck, you'll know at least where you were when you got stuck, so I can help you even more next time. With just some overview of like what the schematic is doing. On your left-hand side, we have your inputs. So just like that block diagram, we have all the different inputs. We have the two switching supplies in the middle. The input selection is down here. I'm using a lot of nets just because I don't want to draw a lot of wires between all the inputs. It would be all messy. We have some indicator LEDs and all the output connections. So as you can see, everything's pretty organized into logical blocks. I'm using lines to actually denote different sections. So the switching supply A and B are different. I have these other lines that are denoting this indicates the primary supply and this is the secondary supply. All this stuff is pretty grouped together, so it's pretty much readable. So this file is also present on the GitHub. It's in the master design reference files. It's the schematic sheet, so if you have that, you can reference it. So your task now is basically to replicate this. So where do you think I would start? The big yellow thing? No, do not start with wires. Yeah, so the first thing is basically getting all the components down. So one of the biggest things is the switching regulator. So in your schematic sheet, go to components. In here, you'll find a component, the LM2576. Double click on that and place two of them on your sheet. There are a bunch of other supporting components around it. Some of them do have specific designators like REF. Those have specific meanings, but some of them don't. It's just 1K, 10K, 1K. The reason why they're different is I want a specific capacitor with a specific footprint, so I need to denote that part number. Sometimes I really don't care what part I buy, I just need it to be a 1 kilo ohm resistor, so I say 1K. In the component list that I gave you guys, there is resistor, like generic resistor, and some of them have the full name. So here's the REF capacitors. Here's the inductor that goes here. Also to rotate components, space bar, pretty neat. X, Y for mirroring stuff. You can select multiple components, copy, paste. Altium is a pretty nice modern program. You won't really have to worry too much. Apparently copy pasting was broken a couple decades ago. Should be fine nowadays. It will throw errors if you do that. But yeah, placing all the components is the first step. Placing them logically where you think they'll connect. So if you go back to the PowerPoint, you can see this is the reference schematic that we're going to be going off of just for the layout of the switching regulator. So if you look between how I laid it out, it's pretty similar. So we have the input capacitors, a couple signals to the ground, the diodes, the inductors. This is an extra filter on the output. If you like low-pass filters, this is just something that the datasheet recommends, which we will talk about next time when we're actually building a part. This I've moved up to the top just for clarity and also space because I wanted to put an LED here. But once you get all your components down and you can move these together logically around, wire them. So like I showed you earlier, you can use wires and you just connect everything together. Oh, that one's not very lined up. Hi, Nick. But yeah, just connect everything together. And that's basically the fundamentals of schematic layout. Making stuff like this and connecting everything logically is probably where you'll spend a lot of your time, because if you make mistakes in this step, they will propagate throughout your entire project. I've left projects where I just didn't connect the signal, guess who was scraping up a trace and putting a bodge wire in? This guy. So use the reference schematic or reference diagram that I have. And yeah, you're free to design stuff like that. If you have any other questions, you can email me or Discord me. I'm on the Discord if you haven't joined that already. But yeah, any other questions before I send you off? Or questions about what we're going to be doing next time? I think we're all good. So yeah, work on the schematic. If you don't get too far, don't worry. Next time is going to be mostly just working through the schematic step by step, talking about components. And yeah, thank you all for coming. I'll be up here for another 5-10 minutes and then I'll head off.